Hi everyone, welcome to this week's video where we'll be talking number theory. More specifically, we'll be covering greatest common factors. Now, before we actually move on with that, let's define a factor, since I'm pretty sure that's what you're wondering right now. So, very simply, a factor is a set of numbers that can divide a given number without leaving a remainder. So let's look at an example to help us understand this definition. So list the factors of 18. 18 being the given number, right? Now, we want the numbers that can divide this cleanly, meaning we are not left with a remainder. In other words, we're not left with a number that has a decimal or a fraction. All right, so of course, let's just go through the list starting from 1. Of course, 1 makes it onto the list because 18 divided by 1 gives us an integer without a remainder. Same thing with 2. 18 divided by 2 gives us 9. No remainder there. Same thing with 3. But then we skip 4 and 5 because that will give us a decimal number or a fraction. And then we can move on through the list. 6, 9, and then 18. Now, these are all the natural factors of 18. But when you think about it, in this definition, it doesn't say anything about natural numbers. It can be any integer, of course. So if this is true, that these are the factors of 18, then these are also factors of 18. Negative 1 times negative 18 definitely gives us 18. Negative 2 times negative 9 gives us 18. And negative 3 times negative 6 also gives us 18. With that out of the way, let's actually talk about greatest common factors, GCF for short, and more specifically how to find them. So before we actually do that, again, definition, the GCF is the largest factor that two or more given numbers share between them. So let's look at an example here. What's the GCF of 18 and 24? So what I'm going to do is I'm going to do the exact same thing that I did in the previous slide and just list all the factors for both 18 and 24. So we had this on the previous page. Now for 24, same thing, just different numbers. And again, you could go through the list yourself, but 24 divided by 1 gives us a no remainder. 24 divided by 2, no remainder. 24 divided by 3, so on and so forth. All of these don't give us a remainder. Now, the GCF here, how to find it using this method would be to go through the list backwards and finding the highest number that they have in common. So obviously, 18 is not found here, neither is 24, so that's not the greatest common factor. 12 can't be found on this list. 9 only on this side, not on this bottom one. 8, same thing. And then we find that 6 is the biggest factor that they share together. So we'll just highlight that. And we know now that the greatest common factor between 18 and 24 is 6. This method definitely works, but it's not very efficient. It's quite time consuming considering that, we might have much bigger numbers than these. 18 and 24, we could list off the factors in a matter of seconds, but if we're working with triple digit or quadruple digit numbers, that's going to be quite tough and quite long to do. So there is a much better method to find the greatest common factor, and that is by using factor trees. So what's the GCF of 135 and 150? Again, we can use method 1 from the previous slide. List all the factors for 135. We'll list all the factors for 150, but we'd be there for a couple of minutes, and that's not time we have. So let's do factor trees. Start off with our two numbers, and then we just break them down into their prime numbers, right? So 135 can be broken down into 15 and 9. Neither of them are prime numbers, so we can continue breaking them down, starting with the 15. Break them down into 3 and 5. Now 3 and 5 are prime numbers, so I'm going to circle these. I'll explain why I circle my prime numbers. These are the ends of my roots, of my trees. Now we go back to the 9. That's not a prime number. We could break it down further into 3 and 3. Those are two prime numbers, circle them. And we've finished. All the ends have circles. We know we're done. Let's move on to the 150. Break it down into 50 and 3. 3 is a prime number, so circle that. Now we move on to the 50. Break it down further, 5 and 10. 5 is a prime number, circle it. 10 can be broken down into smaller parts. 2 and 5 are our prime numbers, circle that. Now, this is why I tend to circle my prime numbers at the end of the roots, and that's because not all of them are going to look this neat, where they all end at the same time. Some of them are going to look like this. Now, it's important to note also with factor trees that you can make it how you want. I didn't have to do 50 and 3 to start off my tree. I could have done it multiple ways. If you wanted to do 25 and 6, that would have worked just as well. You would have ended up with the same primes and the same number of prime numbers. All right, so from here, we move on to our next step. We're looking for the GCF of 135 and 150. And essentially what I'm going to do is I'm going to look and see which prime numbers are common in both trees. And if you notice here, we have a 3 that is common to this 3 too. So what I'm going to do is I'm going to cross them out. They are common to each other. We can list that. Next step, let's look to see if there's anything else in common. Well, I see that there's a 5 here, and there's also a 5 here. So let's cross those out, and let's list it. Now the next step, see if there's anything common again. Now we have a 3 here, but no 3 here. So we can't list this 3. We can't cross it off. And of course, if this one can be crossed off, we can't cross this one. And that would be the end of our road. Be really careful not to cross this 3 with this 3. These 3 are within the same tree. They're not common to this tree. All right, and then of course their GCF would be simply to multiply these two numbers, and we're left with 15 as a product. So as you can see, I can efficiently find the GCF of two large numbers by just simply whipping out a tree. And these trees, as you do more of them, the faster they go. All right, let's take this to a whole other level and find the GCF of three given numbers. So here we're looking for the GCF of 660, 275, and 330. Very large numbers. So we're going to start with the same method, same way we started our last problem. List all three numbers and produce a tree. So 660 can be broken down. So we have 30 and 22. And again, you could have had any other number. You could have had 66 and 10. That would have given you the same final tree with the same prime numbers at the end result. So it doesn't matter how you break it down. You go with what makes it easier for you. So let's break this down into all of its prime numbers. 30, circle our prime numbers, continue with the 10. Let's work with the 22. And there we go. Our first tree is done. Simple as that. Working with the 275. 11 is a prime number, of course, so we are only working with 25 here, and that one is pretty quick. 330, same thing, relatively painless, and we're left with these three trees. And we're going to use the same method as before, simply crossing off what is common to them and then writing them down for our calculation for the GCF. So let's look at what's common here. We have a 3 here, no 3s here. We have, so right away we don't have to bother looking at if there's a 3 here because there's none here. They have to be common in all three. We have a 2 here, but again no 2 here, so we could eliminate this 2. We can't use it. Not common to all trees. 5 is common to this one. All right, so that's a good result. Let's see if we have it in the third tree. We do. So that's our first common prime number. So let's cross it out and let's write it into our calculation. Again, a 2, can't use it in this one, so we leave it alone. Let's look at 11, our last one. We have 11 here. an 11 here, and an 11 here. So it is common on all three trees. Let's cross it out and let's write it into our calculation. So we've gone through all the prime numbers here. It doesn't matter if there's a 5 here we didn't look at, because automatically we know this one doesn't have any more 5s, and we know this one also doesn't have any more 5s. All right. Now we do have a 2 here from before and a 2 here, but again, because this one does not have a 2, we cannot do anything with it. All right, so we're left with 5 times 11 giving us 55 as a GCF between all three given numbers. That's it for today's video, everyone. We're going to look at LCM, lowest common multiples, in our next video, so stay tuned for that. Bye.